In this lecture, we will discuss about a new class of accelerators, basically the colliders. Colliders are the accelerator which actually collides the beam. Means basically one collider consists two accelerators, and in these accelerators, two counter rotating beams are accelerated, and then head-on collision takes place. And at these head-on collision locations, detectors are placed to record the events. So colliders may be linear accelerator based colliders or synchrotron based colliders. Presently, all the colliders except one is based on the synchrotron. The very first collider is the linear accelerator based collider. Actually, accelerator's journey started with collision experiment. Recall the Rutherford's experiment. In Rutherford experiment, he bombarded alpha particle on the gold foil. Means some type of collision experiments was there. And with this experiment, he deduced the nuclear model of the atom. And later he envisages that if higher energetic particles would be available, then nucleus also can be broken or nucleus can be split. So by inspiring these kind of things, Cockcroft and Walton built the first accelerator. That was the DC accelerator. And using the beam of these DC accelerator, they splitted the lithium ion. So accelerator's journey started with the collision experiments. However, later on, it was shown that in case of fixed target experiment, means we have some accelerated beam of charged particle and we are hitting on the target, rather than if we have two colliding beam, we will get much benefit out of the energies. So higher and higher energies and colliders building started. Why higher and higher energies are demanded? So there are two reasons about that. First of that if we have higher energy, means de Broglie wavelength will be smaller. De Broglie wavelength is lambda is equal to h by p. So as p is higher, means lambda is smaller. So we get a better resolution using high energy beam, because each particle is associated with some de Broglie wavelength, and de Broglie wavelength has been reduced due to high energy. So resolving power by analyzing those waves can be increased. The second is directly related to the E is equal to gamma mc square. M is the rest mass of the particle. So if we have very high energetic particle, it can be converted into a more massive particle. Mean more massive particle can be generated using very high energy beams. So now in this lecture we will see one of the important parameters which has to be optimized for making the collider, and why really colliders are needed, means how much benefit we are getting out of the fixed target experiments. To see why colliders are needed, we recap some of the things of the relativity. We all know that these are the Lorentz transformation. This is unprimed frame and this is the primed frame. And primed frame is moving with respect to, there is a relative motion with the speed v in the x direction. So x coordinate will transform according to gamma x minus vt. Gamma is relativistic gamma factor. Because there is no motion along the y and z axis, so these axes will not change. And time is also relative. In Newtonian mechanics, time was absolute, and this was the fundamental change by Einstein, that time is also relative. So from one frame, the other frame time changes by this formula. There is gamma t minus vx by c square. Vx appears because motion, relative motion is along the x-axis. Now you can see that instead of v, we can write down beta c. So this transformation will be x prime is equal to gamma x minus beta ct. Similarly, in the case of time, here we can see that we can multiply this time with c. So this will be ct prime. So here in RHS also we will multiply speed of light c. and here instead of square this will be c, because one multiplication of c is there, and this will ct prime is equal to gamma ct. Again we will write v by c as a beta, this v by c as a beta. So now you can see that transformation of x in this new notation is similar to the transformation of ct prime. So ct prime can be used as the fourth coordinate, and in this fashion we can make a four-dimensional space in which one dimension is by the ct prime, a ct or ct prime. So we can make three-dimensional, instead of three-dimensional vector, four-dimensional vector in space-time. So now we take x0 as ct, x1 is equal to x, x2 is equal to y, and x3 is equal to z. So above equations can be written down as x0 prime is equal to gamma x0 minus beta x1, x1. This is the relation we obtained from here because x0 is ct. So at the place of ct prime we have written x0 prime. Here it is ct, so this will be x0 and x will be written as x1. Similarly, this equation will be written down as x1 prime is equal to gamma x minus beta x0. These two relations will be there for the y and z. So in relativity we can form a four vector. Relativity can be understood without going into the four vectors. However, four vectors provide a powerful way of analyzing some problems, and it also opens the way for understanding the GTR. Now we see the beauty of these four vectors. If we multiply these four vectors together, we get c square t square minus x square minus y square minus z square. There is one rule that you have to put minus sign before the space-like vectors, space-like components, and time-like component will have positive sign. Means you can see that this has been initiated like this. We can write down x, m, x, t, and m is the Minkowski matrix by which we get minus sign here. So in this way, inner product of the four vector is defined. Four vectors inner product definition is this: c square t square minus x square minus y square minus z square. Any quantity which can be represented by four vectors in the relativity will have this formulation for their inner product. Now, what is the beauty of this inner product? We transform this four vector inner product into the another frame. So let us say that in primed frame it is defined like this: c square t prime square minus x prime square minus y prime square minus z prime square. Now we transform it into unprimed frame. So at the place of t prime we will put ct minus beta x, and at the x prime we will put gamma x minus beta ct. Y and z will remain unchanged. When we will open this, c square t square beta square x square minus 2 beta cxt, here we will get x square plus beta square c square t square minus 2 beta cxt. You can see that this will be cancelled out by this, and take the ct square common from this and this, so you will get gamma square 1 minus beta square c square t square, and similarly gamma square 1 minus beta square with x square, because x square term is this and second x square term is this, so you will get 1 minus beta square here also, minus y square z square. 1 minus beta square itself is 1 by gamma square. So this will be cancelled out by this and this will be cancelled out by this. So you will get c square t square minus x square minus y square minus z square. Means this inner product which is defined in this way is Lorentz invariant. It remains constant under the Lorentz transformation. And similarly, for the energy or momentum, we can define four vectors by taking the first component as E by C, then space component Px, Py, Pz. So their inner product will also be a constant under the Lorentz transformation, or it doesn't vary under the Lorentz constant. It is an invariant. Due to this invariancy, we can put momentum and energy conservation law in a very compact form, and it can be used when we study the collision in the colliders. So this will be E square by C square P dot P, the inner product of the four momentum, E square by C square minus P square. This P square is this space-like component, and this is the time-like component. So space-like component again has minus sign by our definition. Now you can see that this E square minus C square minus P square is equal to M square C square, because we have E square is equal to C square P square plus M square C4. So this quantity becomes M square C square, and M is the rest mass of the particle. It is invariant, so this quantity is invariant. So this is an Lorentz invariant quantity. Now in the beginning, studies were carried out using the bombardment of high energetic particles on the fixed target, like the Rutherford. Rutherford also bombarded particles on the fixed target. That fixed target was the gold foil. And later on, high energetic particles ejected from the accelerator and then sent to the target and having the collision experiments. However, in 1956, the concept of colliding beam experiment emerged, that we have to have, instead of fixed target, two colliding beams. Means target is also a beam. So two beam which is having high energy will be colliding. That's why collider is also known as smashing machines. Now, what is the use of collider? Means instead of fixed target, what benefit we get out of the colliding beam? Suppose in the collision of two particles, we have mass m1 and m2, and the center of mass energy can be written down as this is again, this we have written down E square by C square minus P square. This is the inner product of four momentum which we have calculated in the last slide for the two particles. For the two particles, total four momentum will be P1 plus P2, and we have the square of this. This is the invariant, means in the center of mass and left frame, both will see this the same quantity. So this will be 1 by C square E1 plus E2 square minus P1 plus P2 vectors and their square. Now in the colliding beams, because these beams are moving in opposite direction, so we have P1 momentum is equal to minus P2 of the momentum. Means P1 is equal to minus P2, because both the beams are moving in the opposite direction, and then they will have collisions. So P1 P2 square will be, this term will be 0 because of the P1 is equal to minus P2, and we are having only this term. In case if collision is taking place at same energy, means both particles are having the same energy, say E1 is equal to E2 is equal to E, then we have this 2E. So 2E square by C square is the invariant, and it means energy is 2E. 2E is the energy available in center of mass. So if two particles having same energy E and are colliding in the collider, then the center of mass energy will be 2E. This center of mass energy is available for the new events. So for new events means new creation of the particles, for that total energy of 2E is available in this case. Now we compare this case with the fixed target experiment. In fixed target experiment, the second particle P2, which is in the target, is fixed. Its momentum is 0. So for square of the 4 momentum, the length of the 4 momentum will be E1 plus E2 square upon C square minus P1 square. P2 is 0 here. So this will be E1 by C square, E1 square by C square, this P1 square, we have opened these brackets. So the E2 square plus 2E1 E2 by C square. Now this is invariant for the first particle. So, and this is equal to M1 square C square. We have seen this. This is irrespective of the lab or center of mass. These are M1 C1 square. This is because the second particle is not moving. So E2 will be only the rest energy. So M2 square C square. And the third, at the place of E2, again we will put M2 C2 square and M2 C square. C square C square will be cancelled out. So this is the available energy in the center of mass frame in the case of fixed target experiment. Now again take the case of similar particles, that is M1 is equal to M2, means rest mass are same. Suppose proton-proton collision or electron-electron collision. So both the mass are same. In that case, this equation will be reduced to 1 by C square 2E0 square plus 2E0 E1. Now total energy will be square root of this, which is available in the center of mass. So total energy available is 2E0, E0 has been taken out, so E0 plus E1. So in the case of colliding beam, the available energy was 2E, while in the fixed target experiment, energy available is this one. This is much lesser than the colliding beam energy. We take an example for calculating this. Consider that a 7 TeV proton hits another 7 TeV proton. 7 TeV is the energy in the LHC, Large Hadron Collider at Sun. Therefore, available energy in the colliding beam facility will be 14 TeV, 14,000 GeV. Now consider that instead of 7 TeV, we take a 14 TeV proton and hits on the fixed target. So available energy we can calculate using this formula 2E0. So 2, I have taken the 1 GeV as the rest mass of energy of the proton, then again 1 GeV plus 1400 GeV. It comes out only 167 GeV. So instead of 14,000 GeV, we are getting only 167 GeV in the fixed target experiment. So compared to fixed target experiment, colliding beam provides a very high energies. Means many fold massive particles can be generated in the colliders rather than in the fixed target experiment. There is one comparison in this table. Suppose proton and proton hits with 7000 GeV, 7 TeV, which was the above example. So in the center of mass, 14,000 GeV is available, and in the fixed target experiment, it is only 114 GeV. Here we have increased the energy to 14 TeV of the single proton. Here it is calculated for the 7 TeV. Suppose 100 GeV electron impinges on the 100 GeV electrons. So in center of mass, in the colliding beam facility, 200 GeV will be available. While in the fixed target experiment, only 0.32 GeV will be available. And if proton hits the electron, one at the 30 GeV and another at the 20 GeV, these are the numbers closely of the HERA collider in the Germany. So center of mass energy will be available as 235 GeV in the case of colliding beam, and in the case of fixed target experiment, this will be only 7.5 GeV. One should go through this reference. It beautifully describes these things.